You're recording? Okay. All right, so welcome back. Try and cover a bit of material today, just because we didn't get quite so as far as I'd hoped last week. So we left off looking at 3D graphics last week, so we're just going to finish covering that. So actually, let me just quickly, hopefully it's still here, that looks like it. There, so just to refresh our memories, whoops. Oh, the material is still on here, maybe I'll just use this presentation. So we were looking last week at transformations and stuff like that, rotation, translation, so on and so forth. We talked about push and pop in the transformation stack and how we can save the state of the current stack with push and then recover the state with pop. And we briefly finished up with talking about scene graphs, which is basically another way to display data that we're not going to look at in this course, but it's worth knowing about because if you're doing complicated scenes, it makes it a lot easier. And if you're using things like Unity and stuff like that, they're essentially using a scene graph internally. So moving on from there, we're going to look at just a few more topics in computer graphics. So we'll start with looking at 3D viewing. So essentially, when you're talking about 3D graphics, obviously the screen that you're rendering to is a two-dimensional plane, and all the points you're dealing with are in 3 dimensions. So in order to get them from 3 dimensions to appearing on our screen looking like how we want, there's a few various projections which happen, and depending on how you want the projection to look, you can set up the window in various ways. But essentially, you have something which kind of looks a little bit like this internally going on. So you have the concept of a camera in OpenGL and stuff like that. There's not actually a real camera, but you have the concept of it, which actually just changes the rest of the world and so on. But you can imagine like there's a camera, like a digital camera, point-and-click camera, whatever, looking out at the real world. You have some object in the real world, which is your 3D geometry. The camera has what's known as a view volume. So the view volume is basically the perspective from the camera. So a typical pinhole camera like you get with a digital camera or whatever has a perspective view volume. So as you look out, objects in the distance are further away. Objects which in the distance are smaller than objects which are close to us, and lines which are parallel in the real world tend to diverge out to, or diverge or converge into points, but they don't remain parallel. So you have this view volume, and the last thing you have the clipping window, which is, essentially you can think of like a plane which all your points get rendered to. So you have clipping planes. So anything which is in front of the clipping plane doesn't get rendered because we say that it's too close to the camera to see. And then you might have a rear clipping plane as well, and everything out which is further than that won't get rendered because we say it's too far away from the camera to see. But really it's just to reduce the amount of computation we have to do. But this is the sort of thing we have. So we have a camera looking at some 3D geometry, it has a view volume, and we have a two-dimensional rendering of what we can see through that window, what we can see from the camera's viewport, which gets drawn on the screen. So as far as positioning the camera, there are multiple ways of doing it. So the easiest one is this camera line in processing. So basically we have this camera thing which takes 9 different variables. So the first 3 are the eye position. So let's say we have some 3D geometry, and let's put this at, borrow this. So let's say 0, 0, 0 is the center of this point. We have some geometry which sits in the center of the point, and then by specifying the eye position EX, EY, EZ, we basically position our camera in the real world as well. So we can push it as far back as we want, which will obviously make the object smaller. We can move it to the left or right, which will move the object to the left or the right of the camera position. Then we have what's known as the look direction, so the center of where the camera is looking. So the camera we put the camera here, but by default it'll just be facing in the same. Actually, I had a webcam here. This would be slightly easier to demonstrate. There used to be one. Yeah. Oh, there we go. Easy peasy. So there's our camera. So we position it in 3D world with the I, X, Y, Z coordinates, and then we basically specify this center of the camera's vision as an XY point that it's looking at. So in this case, we might say, okay, we're going to move it to this position here, and then we're going to set its CX, CY, CZ to be 0, 0, 0, which will essentially tilt the camera so that it's looking down at the object. So you might say, well, with those two things, we know where our camera is, we know where it's looking, what's this last thing for? This is what's known as the up vector. So essentially, if we specify that the camera should be here and looking at that point there, we're not actually saying which direction is up on the camera. So this and everything else is a valid up vector. So essentially, we just specify which direction with respect to the world coordinate system is up. So usually 0, 1, 0, so that the camera will be facing that way, not that way, or anything else. So unfortunately, I haven't had a chance to double check the locations of these demos. I'll see if we can find them. So file, examples, camera. And so you see in the camera example we have, here we go, pretty much what we're looking at. Hopefully it'll run on this machine. There we go. So we have our object, which is just a box floating in three-dimensional space with some axis coordinate system lines in, and as I move the mouse from top to bottom, it changes the position of the camera. So let's have a look what's going on here. Setup is the usual thing, 640 by 360 using 3D mode. Background is, or the fill color is 204. Turning on lights, so we have this nice lighting effect on the cube. And then the camera, we're positioning it 30 units off to the side. So you'll see here, the box isn't flat on to us, it's slightly off to the side. So essentially we've got the box here and we've actually moved the camera slightly around that so we can see slightly to the side of the object. Then the Y position is relative to the mouse Y. So when the mouse Y is at the top, we are essentially like on the same plane as where the cube is. But as the mouse moves down, we're essentially moving the camera down this way. But because it's always looking at the same object, effectively as it's moving down, it's also rotating up to look at the object. So that's why you get this effect that as it looks down or moves down, the object sort of rotates away from us as well. And then the Z value, which is the distance of the camera in this direction, is always set at 220. So essentially at the start, we are 30 units this way, 0 units up and down, and 220 units out here. And then as we move the camera down, essentially the camera moves like this, but because we've told it in the second line to always look at 0, 0, 0, it's actually going to essentially rotate as it moves down so that it's always looking at that object. And then the last one is, as I said, you specify the up vector of the camera. So in this case, up is relative to this vertical line here. I could, if I changed it to be like this, essentially it looks like it's rotating the other way, because now instead of the camera being like that, it's like that. So it's still moving downwards relative to the object, but because now the image is on the side, it looks like it's actually rotating sideways. So it's kind of a bit, can be a little bit complicated to figure out quite what's going on. Actually, if I maybe oops. Maybe I can illustrate that up vector a wee bit better. You want to remember the command to do the stroke color? Yeah. No, actually, you might be right. I think it is just stroke, isn't it? There we go. All right, so if I make all of these different colors, just to illustrate, it's a little bit hard to see otherwise. do red, green, whoops, and blue. So now if you look, red's top to bottom, green's left to right, and blue's sort of facing towards us when the up value was this way. When I move this back to how it was originally, these should have rotated around. So now red's left to right, green's top to bottom, and blue's facing us, because essentially we've rotated the camera from that position to that position there. So yeah, it's kind of doing it this way is kind of the opposite of what we've been looking at so far, where we position geometry in 3D world. Now we're positioning the camera in the 3D world. So the two of them are kind of doing the same. You'd often use both of them. So you position all the worlds, all the objects in the world with respect to each other, and then you position your camera in the world. Doing this sort of stuff makes it a lot easier if you want sort of a fixed world but some sort of navigation through it. So say you're making a game, like a first-person game, you could essentially set up the world as you would, you know, put all your objects in the right places, and then you just move the camera through. You don't need to keep track of where the person is and draw all the object, or where the origin is and draw all the objects relative. You just draw them relative to each other and then move the camera through the world. Right. So the next thing to look at is view volume. So I said here, this is a perspective view volume. Objects which are further away from the camera appear smaller in its viewport. Parallel lines in the real world aren't parallel in the viewport. They sort of converge or diverge. So there's two main ones which you're going to encounter. There's the perspective view volume and the orthographic view volume as well. So the view transformation transforms the world coordinates into a camera-centered I-coordinate frame. So essentially it converts all those 3D points into some view volume that you can then render to a 2D screen. So this is the perspective projection, and we create it by calling perspective, and we specify the field of view, or the Y field of view of the camera, so the vertical field of view of the camera, the aspect ratio, which is the width and the height of the frame, and then two clipping planes, the near plane and the far plane. So essentially, we have our camera here. We will only render objects which exist within this view volume. So anything which is up here in the view volume will be off the top of the screen, down here will be off the bottom of the screen, to the right of the screen, to the left of the screen, and anything which is closer to this point will essentially be clipped off. So the reason we do that is oftentimes if you've got an object here, or you've got your camera and an object here, you might not want to render it because you're not going to be able to see anything. So you basically define a clipping plane to say anything which is behind this plane we just won't render. We'll assume it's too close to the camera. And also that aids for computation. So if you've got a lot of geometry, you can, before having to convert it from the 3D coordinate system to your 2D coordinate system, you can just say, okay, well, if it's not in this box here, let's just throw it out. And it's the same thing for the far clipping plane. So anything which is further than that far clipping plane away will not get rendered. So, you know, if we had the entire planet sampled, for example, we could just define our one clipping plane, and rather than drawing everything in the planet at one go, we'd only draw whatever exists within that view volume. So that's the perspective projection, which is, you know, a lot easier for us to understand, generally speaking, because it's how we perceive the world when we take photos. It's what the world comes from. The other projection which you're likely to come across is this orthographic projection. So an orthographic projection is essentially a box. So the other one was sort of like a pyramid. This is just a box where everything is the same size regardless of distance. So if there's no camera in this, but if you can imagine that the camera was here and these two objects were here, you know, identical objects, you usually assume that objects which are farther away are going to look smaller. When you render an orthographic projection, they will actually be the same size. And you create an orthographic projection essentially by just defining these parameters here. You might ask, what is an orthographic projection good for? Well, I find it incredibly good for debugging, because often if you're dealing with a small object which is far away, it ends up being so small you can't see it. In an orthographic projection, every object will be the same size. The orthographic projections retain things like parallelism, so parallel lines in the 3D environment will still appear parallel in an orthographic projection, where they won't in a perspective projection, and so on and so forth. So let's just, before we get too much further.
It's good to get an idea of scale as well.
Yeah, yeah. So let's have a couple of examples. So this is one which compares, by the looks of it, an orthographic projection. Oh, okay, that makes things unnecessarily confusing, but just ignore this. I think it's just changing the, yeah. So when I move the mouse from left to right, it's just changing the back clipping plane. So that's why parts of the object are starting to disappear, because here the clipping plane is a lot closer than it is over here. But what I actually want to show you is this is a cube rendered in orthographic projection. So it looks a little bit unnatural. It kind of looks a little bit like an optical illusion. But you can see things like parallelism is retained. So these two lines are parallel, these two lines are parallel, these two lines are parallel, and so forth.
Are you using 3060 there, right?
Sorry?
Degrees on the base from the, if you had a horizontal baseline,
Mm-hmm.
the base of the cube goes up at a 30-degree angle on the left hand, going left, and going right, it would go up 60 degrees.
Yeah, yeah.
Orthographic projections, yeah.
Yep. And that's perspective projection. So that looks more realistic for what we would expect to sort of see. So you can see here that, you know, from our view of the cube, it's sort of, these lines all come down to a vanishing point. Those lines all converge to a vanishing point, even though they're supposed to be parallel. So this is how we experience the world. And yeah, and this is the orthographic projection, which retains orthonormality and all that sort of stuff.
It's used a lot in material games.
Yeah. Yeah.
And that's why I was in, because you're just really going left to right, walking around. Out of perspective.
Let's just see what this other one does.
Does that remind me of Star Wars?
This one? Oh, yeah, a little bit. It's funny how much information you can get out from just two boxes. All right, so I won't bother looking at that, because that's just... So you can have a look at this one in your own time if you want. I don't actually have a mouse, and I don't really want to use that sticky one, and plus it's plugged back in anyway. But this one, these are all, I need to update the links in the slides, but these are all under basics camera. So Move Eye is the first one we saw, where we basically position the camera position using camera orthographic, swaps between orthographic and perspective projection, and perspective just alternate or changes some of the functions of the perspective view, so changing field of view, modifying aspect ratio, and so on and so forth. But have a play with that in your own time if you're interested. But yeah, essentially, so just to summarize the sort of camera stuff, we have two main projections which we're ever likely to use. Orthographic, which maintains orthonormality, so parallel lines remain parallel, etc., etc. And we basically create it by specifying the width, the height, the near and far dimensions. So it's your left position, your left boundary, right boundary, top boundary, bottom boundary, near boundary, far boundary will create our volume. And then to create our perspective, we need to specify the field of view, the aspect ratio, and the near and far. And it's essentially like a pyramid which just has been cut off at the near and far. And then we can specify our camera view by IX, IY, IZ. And that's the same regardless of what projection we're in. Is it?
Isometric view have between orthographic and perspective. It's that weird angle thing. It's not quite one, it's not quite two.
Yeah, I think with isometric, often it's actually just an orthographic projection rendered from a certain angle. Yeah. So yeah, like if you wanted to do an isometric, I think you just put it in orthographic and move the camera so that you're always looking at the corner of objects. That's pretty much how they handle it.
So the perspective is where you chop pyramid things.
Yep. So if you want it to look realistic, you're looking at perspective. If you're doing some sort of often like technical drawings and stuff, will be an orthographic, because that way you can look at it and you can actually take measurements and stuff from an orthographic projection where you can't easily in a perspective.
It's a camera analogy to hear stuff.
Yeah, well, I mean, a perspective is basically an analogy for a camera, essentially. Yeah. Right. Does anyone have any more questions about cameras before we move on? Nope. All right. So the next thing we want to look at is color. So we've looked at this already a little bit, how you can set the color of objects and so on and so forth. When you're dealing with 3D geometry, it gets a little bit more complicated because color, the perceived color is relative to a few things. It's relative to the color of the object, it's relative to the color of the light, and well, as many lights as you want. So for each light, you've got to take into consideration the color of the light, the position of the light, the direction of the light. One other thing in there is the type of light. Is it a spotlight? Is it a diffused light? So on and so forth. You have to take into account the geometry of the object, so the orientation of the surface. So we've all sort of seen when you get like even my cell phone, probably can't do it so much for you guys, but if we look at that front on, it looks black, but as it we move it like at grazing angles next to the light, the reflectiveness increases and so on. So the orientation of the surface with respect to both the light source and the camera is important, which comes into the view position as well, because as we look at a shiny object at a grazing angle, it tends to be more like a mirror, as when we look at it direct on, it's not so much. Which comes to material properties, so the coefficients of reflection, how reflective is the object? Is it completely matte like this laptop where, if I move it around, well, there's still like a little bit of reflection if I look at it like this from the sun out the window, but generally speaking, it's a lot less reflective than, say, the glass screen on my phone. What illumination model are we using? Are we using Phong? Are we using Blinn? So on and so forth. And shading models. Yeah. Not going to go into all of this. If you guys are really interested in like super realistic rendering, this is the sort of stuff you should learn about, but it's far outside the scope of this course. You could teach entire courses on just how to light stuff and make it look nice, but for the general thing, you throw a couple of lights on, and if it looks nice, then we're pretty happy with it. So yeah, this is essentially what's happening. So we have a purple teapot, and if we light it with a cyan-coloured light, so it's not coming out so well on the projector, but this is sort of a light bluey, a little bit yellowy, greeny sort of colour coming in, and then we have our magenta colour teapot. The light which actually comes out is blue, and so when we have this, when we light it with this light, we actually see it looking like this. So this is actually quite confusing when you first sort of use it, because you have a purple thing and then you shine a blue light on it and it comes out looking blue, and it's kind of unintuitive, because this is a more true, or more mathematically precise color model than what we're used to in the real world, where we have reflections and sunlight and all that sort of stuff, which you will always see that this is purple with a blue light on it, whereas because we don't represent every light source and everything in the 3D world, it comes through as pure blue. But essentially in a simple illumination model, you're going to have something like the reflected color is equal to our light color, so 0, 1, 1, 1, multiplied by the material color, so 1, 0, 1, 1, and we can see 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, and 1 times 1 is 1, so we end up with 0, 0, 1, 1, and this 1 here is just for the alpha value of the light. But we're essentially, if we just look at this as red, green, and blue, now we've just got the blue color, whereas before we had blue and a bit of, or some blue, some green, and before we had some red, some blue. Right.
That's color subtraction.
No, it's the additive color model we deal with on computers. Subtractive color models when you're printing stuff.
Yeah. Okay.
So yeah, it's more complicated than that though. We have essentially 3 types of light source which can come in. We have what's known as the ambient light source. So that's the ambient light in the environment. So for us in this room, if we switched off all the lights, the ambient light would be essentially what's left over, so a little bit of light sort of coming in through the window and stuff like that. The diffuse light is sort of the light which is bouncing off all the walls and stuff like that. So if we put sort of black filters, or rather black covers, I guess, over top of these lights here, so that the lights weren't actually reflecting or weren't directly hitting us in any way, they were bouncing off the walls. That's essentially what's coming out as the diffuse light, so it's the light which is sort of diffusing off all the surfaces in the room. And then we have the specular light, which is the direct reflection off the light. So that's before when I was saying, if I hold this up so that it's a grazing angle between me and the light source, I basically see a direct reflection of the light source with just a hint of the light source coming through. So, we have our material color as purple here. And when we create a light, we usually can specify its ambient, diffuse, and specular properties, and then these two things multiply out. So, our material is purple, our light's ambient light is almost black. So when we render it, it almost comes out black where there's no diffuse light or anything, no diffuse or specular light hitting in it. Where our diffuse and light is hitting it, so it's bouncing off some other object, or it's sort of the cone of light as it sort of gets more and more diffused away from the spot comes through, we get this blue color, and then our specular is this sort of yellow color, and when they multiply out, we sort of get this reddy, purpley sort of color in here. So both materials and lights can have ambient, diffuse, and specular values. So here they're all the same, and the light they're slightly different, and as a result, we end up with this. This is essentially what's being rendered. All areas which are ambient are black, all areas which are diffuse are blue, and all areas which are specular are red. And this obviously isn't just straight black, blue, red. There's this nice blending sort of coming in, but this is essentially what the values are being interpolated between. All right. So let's have a look at some light examples. Lights are extremely difficult to sort of think about, and it really is one of these things that you should just have a bit of a play with. So yeah, see what you did there. All right, so this is a spotlight. So there's obviously two light sources in here. So we have three light sources in here. So we have a directional light, which is a light which just points in a general direction and sort of fades out, in fact. Should have a look. I'm not sure. Do we have? Ah, yeah. Although we only have one in here. Odd. Types of lights in OpenGL. Sorry, I just didn't realize there was only one type covered in here. Hopefully. That's not that useful. Oh, here we go. So this is, there we go. So this is generally the sort of idea we have. So we have a directional light where we create a light and specify the direction we want it to be pointing. So it's only sort of going in one direction. We have a point light where we define a source, and light just emits from all directions from that source. And then we have a spotlight, which is kind of like a directional light, but it has things like the fall off and stuff like that. So directional light is, well, the examples I've given here, it's like light coming from the sun. So, it essentially is for us, because we're so far away from the sun, all the light's moving in one direction. And yeah, it's all moving in one direction, and effectively it has no sort of cutoff. Like, if I go and look at the top of a tree versus the grass, which is underneath it, effectively they're lit by the same amount because it's such a great intensity, there's no cutoff. Whereas spotlights will light things depending on how far away they are from the spotlight. So this is more like a torch. And then a point light is essentially just a light which lights everything. So if we go back to our example here. So we have, in this one, a directional light. So you can see the bottom of the sphere is lit just under here by a directional light. So down here, oh, okay, you guys can't actually see that. This makes it a little bit easier. So you can see there's a sphere here, and we can see that the bottom of the sphere is lit a little bit. So there's down underneath the sphere somewhere, there's a directional light which is pointing up. If there was a point light, sort of everything would be more or less illuminated, but here, because it's only coming from one direction, it's not really hitting the top. Then we have a spotlight, which is sort of coming in from this direction a little bit, which is making this yellow glow on it. And then we have this other spotlight, which is attached to my mouse pointer. So you'll see, and let's see, so I think the way these work, I need to have a look, hold on. Processing directional light. Let's just have a look at the syntax for them. So yeah, red, green, blue, and then the direction that they're pointing. So you see here, this directional light, that's red, green, and blue. So blue's the strongest color, but it's got a bit of green in there. So we kind of have this light blue-ish color along the bottom. Then we have two spotlights. Where are we? We have two spotlights, and they have the red, green, and blue. They're X, Y, and Z coordinates. So we basically specify where they are. If you remember from directional lights, we don't. We just specify which direction the light is coming from. So it's essentially infinitely far away, like the sun for what it's worth. And we just specify what direction the light's coming from. Here in spotlights, we specify where their exact position is, what direction they're pointing. So it's almost like a camera in that respect. And then we specify the angle of their cone and the concentration. So basically how powerful they are at the center. So here we have this orange light, so a lot of red, a little bit of green, almost no blue, specified, and it's at this position, pointing in this direction, and its cone, so how far it falls away, is pi divided by 2, and it's 600 intensity. And then the other one we have is this sort of slightly bluish color again, so a lot of blue, but quite a bit of green, not so much red, and its position is relative to the mouse Y coordinates, so 360 mouse Y 600, pointing in the same direction as the spotlight, so 0, 0, 0, negative 1, and with the same fall-off values. So when we add these together, you know, the sort of two blues and stuff add together, and it's more blue, but it's lighter, but it's actually more blue than either of them together. And then as we move this up, the blue and the yellow sort of go together to form almost a sort of whitey color, but not quite. And then as we get around the top, we can actually see the true color of the light as being this blue color. Yeah, and the sphere itself, there we go. So the sphere itself is white, essentially. So it's 204 by 204 by 204. So it looks like it's blue, but that's just because that's how it's being lit. The sphere itself is actually white, and then all the lights on it are just different colors. Yeah, so when we want to use lighting, we use lights to turn on the default lighting, and the types of light we can have a point light. So we did sort of cover them, just not in very much detail. So we basically specify the color we want and the position. So color as RGB and position as XYZ. Well, that's actually direction. Sorry, wasn't it? Not position. Oh no, sorry, that's point lights, not directional lights. So yeah, point light, we specify the color of it and where it is, and it will just radiate lights out in all directions. We specify, we have a direction light where we specify the color and the direction, and the light is effectively infinitely far away, but radiating in that direction at this constant sort of illumination. And then spotlight, where we specify the color, the position, the direction, the angle, and the concentration. So color, RGB, position, XYZ, direction, XYZ vector, and then angle and concentration. So angle is how wide the spotlight is, and concentration is how bright it is. I think at the very center of it, and then it has a mathematical model which creates this fallout. So you see, if we go back to this one, it's brighter in the center, and then as it moves out to the end, it sort of gradually falls away. Right, does anyone have any questions about that? No? All right. So it's, again, this is something that I think it's quite hard to sort of just get your head around just by sitting here and like reading some stuff about it. I think it's really something you need to play with and try some different values and stuff to get an appreciation for.
I'm getting a little bit disturbed, really. I think colour into numbers is something getting in the matrix direction.
Yeah, it's definitely not something which is, I guess, sort of intuitive to people.
No.
And I still struggle with lighting anytime I have to use it. So it really is something you often just play with it until you get a nice effect, a feeling that you like. So yeah, the point light and direction light are quite straightforward. Spotlight is a little bit more complicated because we have this cone and the axis direction is D and half cone angle is alpha. So we specify how wide the cone is, whether it's like really bright or if we get it closer and closer down, it's more like a laser. And then the intensity at vertex P, which would be this one here, at an angle of theta is attenuated by spotlight attenuation factor cos epsilon of theta, where epsilon is a constant. So don't have to worry about that, but essentially what that means is as objects move away from the center of it, they essentially become dimmer and dimmer, and there is a mathematical equation for how that works. Yeah, something like that. I'm not sure what, I think it's a little bit different in the mathematics they use, but yeah. Yeah. Right, so that's lights. Moving on, because as I said, these are quite advanced sort of topics, so we'll just go through it. So image manipulation. This should be quite familiar to Murray, I'd hope. So we can load images using this p-image class. Let me just pull up an example. So topics, image processing. Let's start with, extrusion. So we have this p-image class, which we basically store an image in. When we want to load an image into it, we just use this load image, and that returns a p-image. So you see we create a p-image A, we call load image, and that will store that image in A. And then we can do load pixels when we want to access individual pixels. So load pixels and then get X and Y will return, so many windows open, that one. So we can do a.get, or where are we? A.get X and Y, we can do a.pixels and then specify it numerically, but yeah, there's multiple ways to do it. Get's probably the most easy to understand because we pass in the X pixel we want and the Y pixel we want, and we get returned the pixel. But just remember, you have to call load pixels first, and then we can do some stuff with them. So in this one, it basically loads an image, gets every pixel value out, and stores that in this A pixels, which is a bunch of integers. And then we have a bunch of values as well, which we get the blue value of each pixel, and then we plot each pixel in three-dimensional space with we plot them in three-dimensional space from left to right, top to bottom, as if we were drawing the picture, but then we use the blue value, and that defines how far out the pixel should be pushed. So here, it's not a particularly exciting example, is it? Let's see if I've got anything else in there. So this is essentially, this picture here is essentially this image here, but it's been converted somewhat into 3D, and it's essentially the amount of blue in each pixel has been used to sort of define how far each pixel should be pushed back. So that one's not the greatest example with that image there. If you actually look at the slide, here's a slightly more interesting one where it's got there's a person here and a person here, and they're wearing shiny glasses, and the amount of blue in that sort of pushes those images out. So let's do a slightly more interesting example. This one here, and let's do explode. So this pretty much does the same thing. So loads an image, gets the color of each pixel, each pixel in the image, calculates the Z value relative to the mouse X position and the brightness of that pixel, and then draws it in three-dimensional space. So we start off with an image like that, and as I move my pixels along, move the mouse across, it explodes out. And each of those pixels is moving based on the brightness of the pixel in it. So you see really bright values like these ones up here and these ones around here blow away really far. If I stand at this side, whereas other pixels like this dark blue in here and this sort of murky grey colour in here don't move very far at all. So you can do some basic sort of image editing just by using this p-image function, calling load image to load an image into it, and then by doing image.pixels or image.get, we can get each pixel out and do some manipulation and stuff like that over it. So just a few more advanced graphics topics. So texture mapping. So all of our objects so far have basically been single lit, single color object models. That's not particularly exciting. What we might want to do is texture mapping, so we're applying an image to the surface of a model. Basically, we load our image into a texture like this one here, and then we map it by specifying at each vertex in our object whereabouts it should take from that pixel off there. So if you remember when we looked at the RGB cube a while ago, we say at this point we want this color, at this point we want this color. We sort of do the same thing with texturing, except instead of specifying a color, we specify a place on the texture, and that will stretch the texture between each vertex coordinate. So if you could imagine that, this is X many vertices around this cone here, we could specify this is 0, 0, so this point on the texture here. This is 1, 0, and then we'd go all the way around from 0 right up to 1 on the other end on both parts, and then we'd end up wrapping this Coke Classic logo around this cylinder. So the texture function returns a color value at texture coordinates, and essentially it just iterates between values at the texture. So we specify GL text coord. Actually, I think this is, hold on. Sorry, those are the OpenGL examples. I suspect it uses a different, oops, where are we? Here we go. It uses a different one in, where are we? That's not useful. A better one. Oh, right, there we go. Yeah, so, sorry, I'll change the slides before I put them online. But basically we can specify our vertex now, and we give it the XYZ position of the vertex, and we also specify whereabouts on the texture you want to take the texture from. So 0, 0, 1, 0, 1, 1, 1, 0. So for this face, or for this, face of the, next one, of this cube, so this is a cube we're looking at here, we'd basically be taking 0, 0, so the first one would be taking from here, 1, 0 would be taking from here, 1, 1 from up here, and 0, 1 from up here. So that would essentially map this texture to this face here. So if we run this now, oops, so we can actually drag that around. So this is just one where they've essentially loaded in, where are we, this p-image text, and we load image just like we saw before when we were doing image editing. We have a p-image, we load an image, and then when we go to draw our cube, we basically call texture with text, and that will load that into the OpenGL texture buffer, and then we can just start drawing off it. So we draw the front face and we specify the textures, and if you look for these, because we're using the same texture on each one, we never actually change texture, and they're just using the same mapping each time around. So we'll have a look at what's some slightly more interesting one. So cylinder, so it's the same thing. We have our image Berlin 1, which we load into im, and then we call texture, and then as we draw our tube, we basically specify our X, Y, and Z values for each of the tube values, and the texture coordinates of 0 or U and image height. So it's a little bit more complicated because we need to specify how far around the cylinder we are at each point, and map that to a number between 1 and 0. Oh, this sort of works a little bit, but think that's more of a bug in the example code, but you can see here, essentially that's now been mapped to, the cylinder, that same texture as before. So essentially, as it's creating each of these vertices around here, so there'll be a vertex here, 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 and basically it's just mapping those between 0 to 1 for the last one. So this will be 0, 0.05, 0.1, 0.15, and so on and so forth, to basically extrapolate around the texture. And we can do that across anything we want. So here's a sphere which is doing the Earth, and it's just been texture mapped. Yeah, pretty much. So that's what's going on behind that. Try and close some of these windows down because this is starting to run pretty slowly. So that's texture mapping in a nutshell. Yeah, so text equals load image Earth, and then texture text, and then when we create our vertex now, we specify the X, Y, Z, as well as the UV positions. And just remember that UV always goes from 0 to 1, no matter how big our image is, it will always be 0 to 1. Yeah, and we've looked at those examples there. And the last thing I want to look at in this sort of graphics component of the course is 3D objects. So there's various sort of ways of rendering or even storing 3D objects. So, well, actually these are just rendering techniques really. So you can render a point cloud. So you see here this little bunny, but all this is just a whole bunch of points in three-dimensional space. So we can very easily render this as points. And as a human, we're really good at pattern recognition, so we can sort of identify that this is a bunny. But you'll notice that none of these vertices are actually related to neighboring vertices and stuff like that. Like there's no telling for the computer that that vertex isn't connected to that one over there. As a human, I can look at that and say, oh, that's a bunny, but computers aren't that smart. So the next thing you can do is wireframe. So this is sort of going up the next level here. We just have points in three-dimensional space with no relation to each other. Wireframe, we need to know which point connects to this point so we can draw lines between them. So this point here connects to this point. Actually, we'll do one down here where it's easy to see. So this point here on the very edge connects to this point down here on the very edge. It also connects to the point next to it. So that way we can draw lines between all of these points, and we can generate something which sort of has a bit more sort of structure to it. So we can look at that and say, okay, I can get a bit more of an idea of 3D structure, and so on and so forth. And sort of the highest level of detail is a polygonal mesh, where we need to know for each point essentially not just its neighbors, but we need to know its surface normal. So we need to know which direction that the face which is attached to it is pointing, and so on and so forth. And by doing this, we can have features such as occlusions. So these all these faces here are occluding the ones behind them, whereas here you can see we can actually see through the wine glass. If we want to do any sort of illumination, texturing and stuff like that, we need a polygonal mesh, but we need to know, more than this one. We need to know how the surface normals and whatnot for each face. We also need to know how points or which vertices are connected to neighboring vertices and so on and so forth. So we sort of have this rising level of complexity from just points to points and knowing about neighboring points, to here knowing about neighboring points and knowing about surface normals and all that sort of stuff, so that when we render it, we can have correct lighting, correct texturing, and so on and so forth. It'll be essentially underlying all this sort of stuff, it'll be the same data. They'll just have far more complicated algorithms of dealing with it. But yeah, regardless of what you're using, everything's still represented in one of those three sort of things. So this is just what I was sort of saying before. So in the most basic version, this point cloud, we have a vertex list for n vertices. So for each vertex, we have the X, Y, and Z coordinate for the vertex. These are sort of the other way around. But yeah, then when we go up to the next one, we need to know how they connect together. Then when we get to the final one, the polygonal mesh, we also have a normal list. which basically says, you know, here is a face and a normal is basically the angle which points out from the center of it, so that when light hits it, we know how light's supposed to bounce off it. And we can do a bunch of sort of neat graphical tricks, like we can color objects depending on their surface normal. So if I have, say, a thing like this, and the surface normal points out this way, if it's pointing towards us, we draw it. If it's pointing away from us, we don't draw it, because chances are we can't see it. And the face list contains vertex indices for each of the polygons. So for this face here, we know that it's made up of this vertex, this vertex, this vertex, and this vertex. As far as getting objects into processing, there are various ones. We're just going to have a quick look at one of these, the Cyto model loader, and we're almost done with this part, and then everyone can have a bathroom break while I set up for the second part. But basically, this is just one processing thing, one processing model loader, the Cyto object loader. So we'll just download that and have a little look at it. And while I do that, I'll just jump in. Where's my documents? Processing and libraries. Sorry, you can get a drink in a minute. Right, so if we dump that in there now. So now we're just like we did with the Control P5 library the other day. We've now loaded our object loader, run processing, and if we go into examples and contributed libraries, there's our object loader, and you see it's got a bunch. Superb. It's got a bunch of different sort of things. So this object loader, the Cyto model loader, doesn't actually do just model loading. It does a whole bunch of other stuff as well. So it can do bounding boxes, calculating directions things are facing, UV mapping, all that sort of stuff. But let's load up one little example. So not really the most sort of impressive example, but if we look at, where are we? That one, sketch, show sketch folder. So these are actually, these objects in here aren't actually being created by, you know, specifying here's a vertex, there's a vertex, everywhere a vertex, vertex. They're actually these objects, these OBJ files, which are being created in a 3D modeling program or something, and the material files which link with them, and the texture files which are attached to those materials, and basically they're all being loaded in. So while this isn't a particularly exciting example, because it's just like a triangle with some chunks cut out of it and so on and so forth, you could load in any OBJ file. Unfortunately, I don't have any other ones on this machine. But yeah, basically in order to do that, let's have a quick look at the code. We import Cyto object loader. We have our OBJ model, so this is the class, and then we just go new OBJ model. We need to do, like if you remember from the Control P5 library, when we create this object model, we need to say this to basically say this is the class that's running in it. So if it has any callbacks it needs to do, I guess for animation or whatever, it can do so. And then we just specify a few other things like what the object is. Not sure what absolute is for, but what we want to, what rendering mode we want to use, so triangles, whatever. This would have been a nicer example if I'd have had this model. As far as I can tell though, let's just have a quick peek. It doesn't look particularly exciting. Whoop. Yeah. Run this and see what this is drawing. Oh, this is a slightly nicer example. So this is drawing a bounding box around one of the models. So by the looks of it, it's loaded 3 copies of the same model in and drawn a bounding box around the middle one. What's that got? Same. Oh, damn it. Same thing. That's the one we just looked at. Same one. This one does some UV mapping, so let's have a look, see what that does. Kind of an interesting UV mapping example where essentially in this the cube's not actually changing at all, it's just changing where it's taking the UV map from. So that goes back to the texturing stuff we saw before here. So essentially the geometry is staying exactly the same, we're just shifting the texture back and forward. Yeah, unfortunately it doesn't look like this one has this little Western girl thing, but you can download your own OBJ file. It's a pretty common format, and load 3D models in and create your own scenes with 3D models and then light them nicely and then move the camera around and have your own first-person shooter game. Not going to go into this at all, really, but if you remember from way back, like last Wednesday, we were talking about how when you're doing 3D graphics, you can use the P3D library or you can use raw OpenGL. This is essentially how you would do that. So you do import processing OpenGL. Then when you do size, you go X size, Y size instead of doing P3D or whatever, you use OpenGL. And then you have this P graphics OpenGL object, which you can then start doing OpenGL calls. P3D covers pretty much anything we're likely to use in this course, so I'm not going to bother looking into it, but it's there if you run up against a wall and you have to use it. Though, I don't know, when you're sort of getting to that point, I'm wondering whether processing is the best language to be using, because the graphics pipeline is probably no longer the problem anymore. But if you really need to do super complicated stuff, OpenGL is there. It allows you to talk directly to the OpenGL renderer. You can make OpenGL calls directly, so if you need to do some special vertex specification or shader programming stuff, to be honest, I wouldn't be surprised if there are libraries out there for processing which do shader programming, so you probably don't even need to dive that deep in there, but yeah. And just keep in mind that because a lot of the drawing calls are handled by processing, a lot of the standard OpenGL calls won't work. So even though you're giving yourself slightly more power, you're losing power in other places as well. So it's sort of this trade-off. As I said, if we're doing advanced OpenGL, we're probably better to move out of processing because processing wasn't really designed for that sort of stuff. Otherwise, there's a few other libraries you might want to use. So GL Graphics is another OpenGL graphics thing, like P3D and stuff, which provides OpenGL texture as well. We can do that through P3D anyway. Post-processing filters, 3D models and shaders in GL shader language, and so on and so forth. So this is a little bit more powerful and possibly a better option than using the direct OpenGL calls, because somebody's done the work of making life a little bit easier for us. And that's its website there. So let's have a little break now, and people can get glasses and drinks while I swap over laptops so we can start looking at processing. Let me see if I can pause this video. Look at that, it's actually working. All right, so moving on to the second half of today's lecture. So we've covered processing in a fair amount of detail now, and some advanced topics and computer graphics and stuff like that. I mentioned sort of at the end that, you know, if you're hitting up against these barriers of, actually I'll turn that light back on as well. If you're hitting up against these barriers of, you know, what processing's able to do. Sorry, I'll dim them down again. Yeah, I can see people starting to fall asleep, so I figured it was time to. There we go. So what's that? Yeah, if you're sort of starting to come up against these walls and processing of what you're able to do with the renderers and stuff like that, it might be time to start considering a different language. And so we're going to do that now. We're going to look at open frameworks. Now, this is only going to be a brief introduction, and we're not going to look too much at open frameworks in general, because you guys, last year we did open frameworks, this year we're trying processing instead, but you will be expected to try open frameworks anyway, and have a go and see how you feel, and, you know, choose what you want. First of all, though, we're going to start with some C++ programming basics. Yay! So we've actually, it's C++ is, you know, for the most part, kind of similar to Java anyway. So we sort of covered a lot of this when we looked at, you know, reintroducing ourselves to programming for the Java course. But essentially, we are going to look at structs, classes, and namespaces. So we've already seen structs and classes in processing. Namespaces is something new. We're only going to cover it because you're going to need to know how to use them, not because I expect you to create your own. But yeah, we look at when to use each one, what calling conventions are used, how to create or creators and destructors, and nesting. So we're going to be using Visual Studio. All right, pull this over here. So this is Visual Studio for those of you who have not used it. So it's Microsoft's development tool. And let's create a new project. So we can start typing some code out and testing it. So unfortunately, it's a little bit more work to get started with than processing. But it's also quite a bit more powerful. Right. So, yes, but you can get it free through the university, at least on your university machine. So, and yeah. So there's Microsoft runs a promotion called DreamSpark, which I have tried, and yeah, it works with Canterbury Email, so you can jump on there and grab yourself a ton of Microsoft software, which is nice. So we have to decide this at a later date, which one we choose to use. But basically, there's various versions of Visual Studio. So the lab and the university has a site-wide access to Visual Studio 2010, which is this one here. Off DreamSpark, you can download, in addition to a whole bunch of other software, you can grab Visual Studio 2012 for free. So these are all the things you can get. There's 2013 on there, isn't it? Well, now. So all these various Visual Studio things, Windows 8.1 embedded, I don't know, Visual Studio 2012, blah, 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 Visual Studio Express, Connect for Windows SDK. So yeah, there's about, it's 2008, that's not really, 2010. Oh, there it is too. Okay, there we go. So yeah, you can get Visual Studio. These are all free and full versions if you're a student. I tested it out earlier at the start of this year, and it appears to be up and running for Canterbury students.
So you have an enter online.
Oh yeah, just put in your student email address. You sign up with your student email address.
That's how they check your student.
Yep, because it has to be at.
Test email, isn't it?
Yeah. So I tested it out and it worked. So yeah, you have the choice of using, well, don't use Visual Studio 2013 because I will explain to you why you have these two choices in a minute, but you can use Visual Studio 2012 if you want. Do I have it? I do have it installed on here as well. So I only have the Express edition on here, which is the free version. You can actually download Visual Studio Express, which is the free version for everyone, which looks like this. So they keep changing the color scheme every time, and I don't know why, and it's incredibly frustrating, but yeah. Well, they were pretty standard from 2005 to 2008, but then 2010 changed, now 2012's changed. Yeah, so you can download 2012 Express for free. As students, you can download 2012 Professional for free. And through okay, let me start again. You can download 2012 Express for free. Through DreamSpark, you can download 2012 Professional and 2010 Professional. And at the university, we have a site-wide license for 2010. But we don't have a site-wide license for 2012. So if you want to use 2012 here, you'll have to get a copy of DreamSpark, or you'll have to use the Express Edition. But yeah, it's up to you. The reason I mention this is because, as I said, we're going to be using Open Frameworks. And Open Frameworks is, I will explain a little bit about it soon, but basically it comes, whoops, that's not really useful. Open Frameworks comes tied to a particular version of Visual Studio. So the latest version, 0.8.1, is, it does say it on here somewhere. Yeah, so 0.8.1, which is the most recent version, works with Visual Studio 2012, not Visual Studio 2010 or 13. It only works with Visual Studio. That's why I said not to get 13, because none of the Open Frameworks versions work with it. If you want to use the latest version, you have to use 2012. Otherwise, if we scroll down to the bottom of the page and you see other releases, there's older releases here. So 0.8.0, Visual Studio 2012, and if we go back to 0074, it's Visual Studio 2010. 0.8.0 is fairly recentish, so not all the libraries and stuff work in the most recent version. So unfortunately, it's not quite as flexible in that respect as processing. You have to sort of say, okay, I'm going to use the most recent version, and I'm going to use Visual Studio 2012, or you're going to say, I'm going to use the slightly older version because there's more stuff compatible with it, and use Visual Studio 2010. I really don't care which one you guys use. It would probably be good if we can consistently use one, but we can talk about that a bit later because it's not super important at this point in time. Anyway, back to here. So now I have set up my project, and I'm ready to start writing code like I would in processing. So let's try void main, printf, hello. And I'll probably need to include so let's just make sure that runs. In release mode, so the window won't disappear. There it go. Try and remember they changed this in Visual Studio 2012, and I find it incredibly frustrating. System console. Don't worry about what I'm doing that you can't see. Bear with me just a second. Where's my mouse pointer gone? As I said, it's not quite as easy to get up and running as processing, but once you do, it's not so bad. Oh, here it is. Okay. Sorry, it was popping up on the other screen. So, all that work, we've now written hello to the console. So basically, same with Java and stuff, processing and stuff like that. You know, you write your things the same, so you might have voids set up, blah, 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 blah. In C, though, the first thing which gets run is this main method. So we can't actually, unlike processing, we can't write something out here because it needs to be within a class, or rather, everything needs to be within a method in C. So it's a little bit less flexible in that respect. But basically, main is the first one which runs. So main is kind of like setup and processing, and then we just write all our code in there. So you see up here, I've had to include standard IO for input output .h, which basically contains this print function in here. So now I can print stuff and it will pop up. It will prop up on the window, which keeps popping up on the other screen, which is kind of annoying. Right, so this is, basically our hello world example in C. So let's have a look now at structs. So we have over here this example of a struct person. Oops. And if we want to use strings, so in processing, you remember we had in processing we had the string thing that we could store names and all that sort of stuff in. It's similar in C, it's just a little syntax a little bit different. So here we have to include our string class first, and then instead of being called just a string with a capital S here, it's standard string. So we have first name, standard string, last name, age. And that is exactly the same, more or less, as the structs we looked at in processing a while ago. Just the syntax is slightly different, but they work in exactly the same ways. So a struct is just basically a collection of data that we want to store together in something because all the data makes sense to be together. So for a person has a first name, a last name, and an age. And then in main, I might say, okay, well, let's create a new person called Adrian. And we'll say Adrian dot, and look at that, we've got autocomplete, hooray. Adrian dot last name, Clark, and Adrian dot age equals 30. You can see I did these lecture slides last year.
You got to know.
Right. So yeah, this shouldn't be too surprising to you guys because this is essentially what we did in processing. So this is a struct. We use it to basically define a sort of object and store a bunch of stuff together. So now we have this person, Adrian. If I run this, it's not going to do anything at all because we haven't told it to do anything. So you'll see in my console window, it just says press any key to continue. Awesome. So that's a struct. Yeah. Any of them. Any of them, any key. You just got to use a bit of twink to change it. Oops. That is over here. Right, so classes are functionally similar to a struct, and they're usually used to encapsulate data and methods that belong to one object. So you can actually do, in C, they're actually pretty much interchangeable, really. I'm not really sure of any differences between structs and classes. But, you know, typically use a struct for just storing a few bits of data together about something. A class you might give objects or give methods to as well. So here, this is exactly the same as we saw in processing. So we have our class person, and we have these things which we sort of looked at before, but now we define these as public. So public means that everything which can access person can access it. And private means that only this person can access this information here. So when I create a new person lecturer, you know, this first name, last name, and age, I couldn't type person or lecturer dot age and get that value because it's private to this class here. So only this class can actually do it. We have constructors and constructors like we saw in processing where it's the same name as the class and we can pass an argument. So down here we say person lecturer, Adrian Clark, and it will store the first name in here, the last name in here, and the age in here, and then we just copy it into these private methods. And in C++, we also have a destructor, which basically gets called when you delete the object. So when you delete the object, maybe if you've opened a file or something in here, when you delete the object, maybe you want to close the file or something like that. And then various methods. So here we have this lecture which prints out blah 10,000 times. Yeah. So, you know, hopefully does everyone sort of understand what's going on here? Does this make sense? So it's pretty much exactly the same what we saw in processing. As I said, you know, this is sort of fairly similar between the two of them.
So is it the logic behind the login?
Sorry?
Login window. Private.
So it's more to do with the data. So if let's jump back to this one over here, and now we'll turn that from a structure into a class, and we have public, and we have void. I can call this print. Yes, I can. And int I can access. And then if we have private void I can't gadget touch typo. Yeah. So it's really, it's less about sort of there's supposed to be an F in there. Format, essentially. So you can do the printf statement. You can do a lot of complicated stuff with. Oh, it doesn't matter. It's like processing white space, doesn't really matter. So now I can create a new person called Adrian. And when I call Adrian dot, so you'll see with the IntelliSense now, the blue basically means it is a method. Oh, sorry, not a method, a variable. And the purple one with speed lines means that it's going really fast because it's a method. I don't understand the convention. Maybe that's supposed to be text, I don't know. But the ones with the locks on them are private or protected, which I'm not going to go into what protected means. But basically I can, because these are public, I can call them. So I can do this. And when I run this, is protected is for inheritance, yeah. So when I run this, it calls, I can call this, and it says, yes, I can. But now if I say Adrian, Adrian dot, I can't call this. And now when I try and build it, it'll say, error, can't access private member. So basically, I'm not allowed to access that. However, in here, we could do, we could say, I can't call this like that. And that will run just fine, or build just fine. And when I run it, it says, yes, I can, no, I can't. So this main method can call this because it's public, but only person can call its own, I can't call this method. So only, it has to be written within the person, between this start bracket and this bracket. Those are the only things which can access private methods. Public methods, anyone can access public methods or variables. Right. So everyone cool with that? Happy? Yep. So another thing we can do is, another thing we can do with C, which you can actually do in Java to a certain extent as well, is we can actually do what's known as interface and an implementation. So you see here now I've got my main.cpp file. Now say I don't want to clug it up with all this person and stuff because I've got a million different classes I want. Let's create a new file and we'll call this person.h. And let's create a new item called person.cpp. And so in person.h, we do what's known as the interface. So the interface basically tells you what methods it has and how you would call them. So in the interface, I might do something like void person, and let's, not void, class person. And let's say, okay, person, let's have a person constructor. Let's have a person destructor, and let's make these public as well. And let's give the person an age and name. And just because we're using string, we need to do that. So now you can see we've basically, if we look at this, we can sort of say, that should be there. If we look at this, we can say, okay, well, there's obviously somewhere there's a class person. It has a constructor, it has a destructor, and this person has an age and a name. We don't actually know what the constructor and the destructor does. We want to hide that from people who are using our code. So what we can do now is we can actually have something where we say, okay, let's say, well, first we need to say include person.h, and then we say person and person. So this is our constructor. Name equals Adrian, age equals 30, And in our destructor, we just go, I died. And in here we'll say printf, I was born. Yeah, I'm getting there. This is how I program. I'm just all over the show. You're just going to have to deal with it. So similar to as we saw in processing as well, if we're accessing something within a class or whatever, we use these two colons basically to say that this person method here is a member of this person class. This person destructor, and we know it's a destructor because it's got the little squiggly line, is a member of person. Now in main I can go include person.h, void main, person p, and yeah. If I run that now. So person P gets created, I was born, and then when main exits, they get deleted, and so it says I died. So you can see now my main CPP thing where all my code is nice and clean. There's nothing, no actual definition of a person or whatever. If we look at person.h, you can see this is basically the functions we can call on a person. So we can create a person, we can destroy a person has an age and a name. And if we want to see what these methods actually do, we can go into person.cpp and see all that stuff in here. So that was my very long-winded way into this. So basically we can do a class, we can have an interface which just defines what you can do with it. The implementation which sort of says, okay, this is how these functions work. And then we can use it just by going person lecturer. And this will essentially look in here and say, okay, what methods do I have? Oh, yeah, we've got a constructor, we can do that. And then when we run it, it'll come into here and it'll run these pieces of code.
What does pragma once do? Right at the top of that?
Okay. This is where it starts getting complicated. So with basically the way this works essentially, sort of the way it works is, so I've written these all into their own files, right? Yeah. When I do this include person.h, it pretty much literally, the compiler will come through and it will go like this. It'll go, oh, include person.h, let's put that in there, and include person.h, let's put that in there, sort of thing. So it basically literally drags all the code through and puts it all where it should be. So to make it nice and easy for us, we can put it all in there. The reason why this gets difficult is, let's say we have a new one, which is a class, say. So now we have a class, and let's say our class will have a bunch of people in it. And in order to be able to use these people, we need to have person in it. We have our class. That's going to get confusing. And then we have person. Yeah, we'll just say we have an array of people in our class, like that. Right? So that's going to complain because I've put those around the wrong way. There we go. So we have a class full of people. So basically, when it's trying to compile it, it's going to come to this one. It's going to say, okay, class. Actually, hold on, sorry. Let's say we want to be able to have a person and have a class in here like that as well. So we could have a person P and we could have a class C. Basically, when the compiler runs, what it does is it goes, okay, let's start with class just because it's easy for us. So, okay, include person.h. So let's jump in here, grab all this code, and replace this with it. And then we go back to main, and we say, okay, so in here we need to replace all this with person, and now we need to include all of class in here as well. And you see now we've got person defined once and twice. So it'll say, okay, we've got 2 copies of person, which one am I supposed to use? So by doing pragma once, basically what happens, so now if we say person.h, we go pragma once. What will happen is when we do, class, when we start compiling it now and we have this, it'll go, okay, let's grab all the content of this one and copy it in here. And then it goes, oh, actually, this is pragma once, so let's just delete what's in there now. And so the next time it rolls it through, basically that person thing will be inherited through the class.h. So yeah, basically if you end up with problems where it's complaining that you've got multiple redefinitions of stuff, it may just be a case you need to put pragma once in there. Otherwise, it just keeps grabbing all these definitions out of the H file, stacking them all in together, and then it's like, wait a minute, I've got multiple copies of this, what the hell's going on? Whereas if you say pragma once, you say only ever include this once, and if you ever get asked to include it again, don't do it.
Person C++ file.
Hold on. It's in here somewhere.
Mm-hmm. Do you use escape characters like \n?
Oh, yeah.
What other characters can you use?
Right, yep. So in, good question. And I haven't covered it because I forgot about it. Because it just becomes second nature after a while. But as Jonathan was saying, so if we go back to this one, let's include io.h. So you'll notice there's two different ways of including files. So you can use quotation marks like this. Quotation marks are used when you've written the H file yourself. And then we've got angled brackets like that. So angled brackets are when you didn't write the H file. So that's pretty much the shortest way to describe that. So that's why I've been sort of mixing and matching. If you've written it yourself, use quotes. Otherwise, use the angled brackets. So as Jonathan was saying, in processing, we have print and we have println. And one of these would print ASDF, and then if we call it again, it would print ASDF. The other one, it would go ASDF, new line, ASDF. In C, we don't have a print line function. We instead use this, what's known as an escape character. So this is an escape character here. Anything with a backslash followed by a character is an escape character. I don't know all of them by a long shot. Oh, this is dozens. C, programming, escape, characters. So there are a boatload of them. But basically the ones you're likely to use are new line. You might want to use horizontal tab, which would just tab out a certain number of spaces, and backslash. So if you actually want to put a backslash in your thing, you have to use // One kind of cool thing we can do about it is, so if I wanted to put something like woof in quotation marks here, whoops, Jesus. If I want to put woof in quotation marks there, I put that first one, it goes, oh, okay, that's actually the end of where his thing is. I can actually escape character my quotation marks, and then it will put them in the text. The dog says woof. That's right. So other ones we might want is if we do that one, we will end up with that slash. That creates a new line. This creates a tab. One, tab, two. So the dog says now woof has got quotation marks. We have that slash from there. We have a new line, and then we have one, and the horizontal tab puts this gap in here for two. So there's a bunch of different escape characters. If you want to do single quotes or double quotes, I've never seen anyone do a question mark like that. But yeah, you can. So yeah, it does. Maybe there are certain circumstances where it does something else. I don't know. Right. So after that, let's just keep digressing a little bit further and talk about templates. So again, we looked at this in processing a little bit when we were talking about our array lists and stuff like that. So a template is compile time generation of code. So I don't want that one. I want this one. So you remember we had in processing we had array lists, and we would say I want an array list of people like that. And in fact it's exactly the same format in C++. This is what's known as a template, and basically we can just define an abstract type. So an array list, we basically, when we write the code for it, we say an array list holds an array of things. We don't say it holds an array of people. We don't say it holds an array of numbers, dogs, apples, whatever. We just say it holds an array of things. And then at compile time, we say, okay, we actually want it to hold people or a person, array of persons in this case. So we pass it in. So this is what templating is. In C, if we don't have array lists, we have what are known as vectors. So we do a vector like that, and we access it like this. So we have a standard vector of ints, my int. So, yep. So, yep. So this could be anything. This could be ints. It could be floats. It could be booleans. It could be people. It could be apples. It could be anything you want. And basically, you see, we're just using the same class each time. Obviously, you'll need to change these names, but we're using the same class each time. And all we're doing is basically specifying what type we want it to hold. So an int, a float, a boolean, blah, 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 blah. Can be done at class or function level. So you either have a class like a vector, which takes a template and everything in that class will hold templates, or you could have a single function. Right, allows writing generic code which handles many different data types. We've sort of already covered that. So yeah, standard vector, int vector. So when we have an int vector, we use, rather than add, we have this pushback method which pushes it onto the back, because vectors are stacks. So we like push matrix, pop matrix, same thing. So push 1, 2, 3. Floats, strings, you name it. We can stick anything we want in one of these. We just have to tell it what we want to store in it.
Is the template the one where if you have, instead of having a method that adds 2 ints together and it's expecting 2 ints and it returns it, you can just pass it in anything and it will add them up and return it back from that thing.
Well, there'd be multiple ways of doing that. So you could do that with a template, or you could do it with method overloading.
Yeah, I was saying with the template, I think it's a lot. The method overloading, not defining each method. Well,
yeah.
But with template, you just define it once.
Yep. Right, and let's just see how many more. I've got a ton of slides, but we're not going to get through them all. But maybe I will just. We'll see if we can get to open frameworks anyway. So we'll finish. We've only got a few slides left. So we looked at structs. So as you remember, structs collect some data together which is related and puts it into one thing. We looked at classes, which are like structs, but we throw methods in there as well. So a person could be a struct if they don't do anything. We just have a name and an age. If they do something like lecture, we might want to make a class, and then we can give them that. The other thing to do is look at namespaces. So namespaces is sort of a more abstract idea again, and it just sort of collects together loosely related concepts. So you might say, okay, let's have a namespace of. Let's have a namespace of objects in this room. So, we have a class for a television, and the television can be turned on, turned off, do a bunch of other stuff. And then in the namespace, we might have namespace of stuff in access grid room. So then we could go stuff in access grid room dot TV dot whatever. The reason I mention this is because we've seen this STD thing before, and that's basically the C standard namespace. So if we go back to here, you'll see where are we? STD vector, there's a whole bunch of other ones. There's STD map, which I haven't included, so it's not going to show up. But there's a whole bunch of these various things. And basically, this is there are just a whole bunch of helpful functions which are worth knowing about, because they're the sort of stuff processing provides with like array lists and all that sort of stuff are essentially covered by C in the standard namespace. And if we have a look at this website, which is a pretty good thing, these are a bunch of different things, which are provided within the C standard library. So let's say I want to do some input-output. I look in here, and here are, oh, actually those are C functions. Where are we? So let's say I want to do some stuff with strings, and I look in here, and these are the classes which are contained in it. So the standard string. I want to do something with localization. So we have this somewhere in here, this std locale class. So there's a whole bunch of various stuff in there that I'm not going to go into, but just worth knowing because namespaces are something that you're likely going to come across quite a bit. And here's an example. So I found this image a while ago, and I thought it was kind of funny. So this is how women define colors versus how men define colors. So what we could do is, if we wanted to develop something which maps from women's colors to men's colors, we can use, just sort of gave the name away, a map. So this maps from one thing to another thing. So here we create a standard map, and basically a map says we map from one type of thing, so a standard string, to another type of thing, another standard string. And here we say, okay, woman color map, maraschino is basically the same thing as red. Cayenne is the same thing as red. Maroon is purple. Plum is purple. Eggplant's purple. Grapes purple. Orchid's purple. And that way we can basically just say woman, man, color map, maraschino, and it'll tell us that this is red. So it provides us a way to really quickly and easily like look up stuff, and that's a map. We've seen strings before. There's two different ways to write text, so we can use that printf, and there's also the cout method. There's vectors. But the reason all of these examples are in here is because you see these as all start std : std : std : std : That's because all of these are members of the standard namespace. So all of these are really useful functions or objects or classes, and they all exist within the standard namespace. The alternative we can do if we get sick of writing out standard all the time, so we have my int vector, my float vector, my bool vector, and just keep those ones because I can't bother writing the rest. So say I get sick of writing std : millions and millions of times, C actually provides you the ability to just say using std, and then it will, using namespace std. And now when I do these here, it'll say, okay, well, let's have a look and see if these are in the std namespace. So it doesn't really sort of provide any benefit other than it saves you writing a few characters here and there, but it's worth knowing about because sometimes it can make, especially when you look at examples like this, standard map, standard string, you know, that would just say map, string, woman, color, man. So it makes it a little bit easier to read. So yeah. In one file, yes. I don't know. I think they can be nested as well. So you could have a namespace inside a namespace. But yeah, it starts getting kind of confusing. So this is the same example again. So if you look, you see standard all over the show here. Here we just say use namespace standard, and it's a lot tidier and easier to read. So we've got a string of type myString. We write myString to cout and follow it by an end line. We've got a vector with ints in it. We've got a map which takes two strings. Yeah, and so the last thing we covered, we've looked at when to use each one. So structs is just, typically if we just have data, we don't have any methods which do it. So we want to describe something, but we don't want that thing to do anything. Classes are like structs, but they have methods, so they actually do stuff. And namespaces sort of just, we use to group stuff together. And we can nest, so we can have, so say we have a struct of type color, and that has a red value, a green value, and a blue value. And so now we can say color blue dot red equals 0, blue dot green equals 0, blue dot blue equals 255. and let's say, okay, well, we really only want to use color within our class of our color wheel class or something. So now we could have something like that, and now we can sort of say, oops, I need to, there. Now we have something like color wheel dot color blue sort of thing. So now you can see that color is a part of a color wheel. We can't just say color anymore. You can see here it's packing a sad. What's that one packing a sad about? Yeah. Yeah. So we'll just make that public so we actually have access to it. Yeah, so now we could do the same thing like that. And then we could have a namespace as well. So we might say namespace my color functions. Which contains all of this. And then we'd need to say my color functions dot color wheel dot blue. Sorry, that actually should be one of those. Like that. So we can nest all these things inside each other however much we want. You can have namespaces and namespaces. You can have classes and structs. You can have... I think the only thing is I don't think you can have a namespace in a class or a struct, but you can have pretty much any other combination thereof. So yeah, whether you ever want to do that or not is debatable, but sometimes it just helps sort of... Yeah, but you can sort of create a nice hierarchy of objects. So you can say, okay, well, you know, we have a color is a part of a color wheel, so let's put the struct inside the color wheel, and then so on and so forth. Yeah. I'm not going to look at UML diagrams, but yeah, it's good for that. Actually, I'm going to leave it there because the next thing we're going to start on is pointers, and nobody wants to look at that. All right, so yeah, that's an introduction to some of the C sort of stuff. We'll look at, starting tomorrow, we'll look at pointers and then get into open frameworks. There's actually only like 5 more slides, but pointers take a fair amount of time to explain. 5 more slides before we get into open frameworks rather, but yes. Yeah, so does anyone have any questions about anything we covered today? I know it was a lot of stuff. I'm just sort of trying to get a bit more back on track from having a few sort of disruptions. Yeah, that's why basically, I mean, your thesis, you guys can do whatever you don't have to use processing, you don't have to use open frameworks, you could write it in MATLAB, you could write it in whatever you want. We're just trying to sort of give you guys an idea of here are some tools out there which may be of use to you, and here's how you use them, and if you choose to use them or not, it's up to you guys. Right. And yeah, otherwise, don't forget the assignment's due at midnight tonight, or 11:55 p.m, and perhaps we'll have a look at them tomorrow. We'll see. Depends on how much I feel like it really. But yeah, I'll put those slides up online as well. I try and always put the slides up like immediately after the lectures. That's right.
Cheers.
No worries.